on exam 1. This material is on homework number 3. So the exam 1 is going to cover homeworks 1, 2, and 3. And this is an early look at atomic structure, but it will segue us very nicely into the mole concept, which will be a set of material that'll be on exam 2, but it's very important stuff. All right, so let's just start going through these. I may or may not break this up into 2 videos, just depends on how long they go. All right. So in early atomic theory, some of the early stuff was coming up with the idea with what are atoms made of, what is matter made of. And so an atom is defined as the smallest piece of an element. And really, the smallest piece of an element, that is still that element. And we'll revisit this in just a moment. A good place to start is Dalton's atomic theory, or really Dalton's hypothesis. It's in the early 1800s. And he based this on some other people's work, but came up with this. All matter is made of indivisible atoms. So if you think of the word indivisible, that means it's the smallest thing. It cannot be divided. That's why the atom is the smallest piece of an element, and that's true. Atoms of the same element are exactly the same. Atoms of different elements are different. And you'll find some of these aren't quite right, but it's a good starting point. You'll see as we progress, some of these are actually a little incorrect now. But for now, okay, and so this means, for example, all atoms of the same element are the same. It means all gold atoms are the same. Atoms of different elements are different. That means lead atoms and gold atoms are different. So the difference between lead and gold is not how the atoms are arranged, it's the atoms themselves. Now, atoms can combine in whole numbers ratios, to form compounds. I have a slide that talks about this. And atoms of the same elements can combine in different ratios to form different compounds. And the last two I'm putting on separate slides. All right, so atoms combining in whole number ratios to form compounds. So if we look at a formula of a compound has the symbols of the elements, and then the numbers with their numbers, and they go with whatever immediately precedes. So for example, these two formulas, this is water, this is called aluminum oxide. Right? The 2 goes with the hydrogen, there's an implied 1. So this is hydrogen and oxygen in a 2-to-1 ratio. Now mathematically, we could say it's 1 hydrogen to half an oxygen. But we can't write the formula this way. And why is that? Because atoms are indivisible. Right? There's no such thing as a half of an atom. Same here, Al2O3, right? This means there's 2 Als and 3 Os. You could write it mathematically as 1 aluminum to 1.5, but again, there's no such thing as half an atom. So that's really all that means, all right? But so when they combine, you have to figure out the whole number ratio, and there'll be some stuff on that when we do, some later on as we progress. Right? And then atoms of the same elements can combine in different ratios to form different compounds. Or if you want to say this just in regular English, you put the same stuff together differently, you get different stuff. So here's a couple examples. So this is water, hydrogen and oxygen in a 2-to-1 ratio. And we know a lot of stuff about water. It's a clear, colorless liquid. It's necessary for life. It's non-toxic. It dissolves lots of things. It boils at 100 degrees, freezes at 0. All right. Actually, water is quite reactive, but still. Okay, this is hydrogen peroxide, and this is the same elements, but instead of being a 2-to-1, it's a 2-to-2 ratio. It's also a clear, colorless liquid. It's toxic. It decomposes in sunlight. It breaks down to oxygen gas and water. You put it on cuts to kill bacteria, right? So again, it's not what are these properties. What I want you to see here is that the same elements, hydrogen and oxygen, put together differently, give you very, very different compounds. All right? So that's those concepts. Now, it turns out Dalton was wrong. Atoms there are actually smaller pieces of an atom, and there are other subatomic particles like quarks and neutrinos and antiquarks and uncle quarks and morons and turons and all sorts of stuff like that. But these are the ones that we use in chemistry. Now let's back up for just a moment. You can see that an electron is very, very small. So I said earlier that the smallest piece of an element is an atom, and that's true. Yet an electron is smaller than an atom. Why don't we say the smallest piece of an element is an electron, or a proton or a neutron? And the answer is actually quite simple. All electrons are the same. All neutrons are the same. All protons are the same. So if I took an electron out of gold and an electron out of lead, and I switched them and put them back, it wouldn't make any difference. So once you get down to the subatomic particles, it's no longer that element. So that's why we can say that the atom is the smallest piece of an element, because the atom is the smallest piece of an element, that is still that element. Once you get down here, it's no longer the element. So if there's a test question, true or false, the atom is the smallest piece of an element, the answer is true. So we're going to abbreviate these P, N, and E. These are the actual masses. You don't really need to know these, but I put these here just for reference. We just call proton a mass of 1, neutron a mass of 1. An electron, it has a negligible mass. So what does that word mean, negligible? Negligible means it's so small we just don't care. So it's such a small amount that it just doesn't matter. Think of it if you were, so like you go into 7-Eleven and you buy something that costs $20. I'm sorry, $19.99, and you give them a $20 bill and you don't wait for the penny change. Did you lose money? Yes, you did. But did you care? No, it's a negligible difference. All right. So electrons do have mass, but it's so small we don't count it. All right. And then as far as charges go, a proton, pro positive, is +1. A neutron comes from neutral, 0 charge. Electrons have an equal but opposite charge to protons, so they have a charge of -1. Now, atoms are electrically neutral, so that means that the number of protons and electrons are going to be the same, and we'll look at that in a moment. Now, in order to do some of this stuff, I'm going to introduce a notation, and we actually don't use this very much except here, and also when we deal with radioactivity, and we're not going to deal with radioactivity in this class very much. I'm just going to talk about it for reference. You'll do a lot more with radioactivity in Chem 201, second semester of General Chem. But in this particular notation, we have the symbol of the element that you get from the periodic table. The atomic number, also called the Z number, is in the lower left-hand corner. But on the periodic table, since if you know the element, you know the atomic number, we frequently don't write this one. In this corner, upper left-hand corner, we have what's called the mass number. It's not the mass, it's related to it, but it's the sum of the protons and neutrons. And then it's not shown on the slide, but right here, if there's a charge, it would be written here. All right. Now this is a periodic table. I've given you one, and you should print this and have one available. Not this one here, but I put one in the module, and it's just a document. There's also one in your textbook. I would have this handy. You're going to need these during exams. Now on this is kind of grainy, but you can see these numbers here: 1, 3, 4, 5, 6, 7, 8, 9, 10, and so on, 11, 12. These are the atomic number. That's the number of protons. All right. It has a huge amount of information that we'll get to later as we progress. Now, so from here, we can look up, if you have a periodic table handy, we can determine the number of protons, neutrons, and electrons from this notation. All right, so if we back up, how do we know carbon has, we'll do the protons first, carbon, aluminum, sulfur, and iron. So if you look, carbon has 6 protons. Doesn't show up very well here. Aluminum is 13. What will be the next ones? Sulfur and iron. So sulfur is right here, 16. Iron is right here, that's 26. You always want to do the protons first, right? So this is the atomic number. I typically don't write them here. Now, how do we know carbon has 6 neutrons? The answer is this is the protons plus the neutrons. So 12 minus 6 is 6. It's really as complicated as when you learn things in 2nd grade. So if you remember in 2nd grade, they had questions like, Johnny has 15 apples and oranges. If 8 of them are apples, how many are oranges? And then you would just subtract. So carbon has 12 protons and neutrons. If 6 of them are protons, how many are neutrons? The answer is there's 6. Okay. Aluminum, 27 protons and neutrons. 13 are protons. That means 14 must be neutrons. So these two are going to add up to that number. 35 protons and neutrons. 16 of them are protons from the periodic table. 19 must be neutrons. 16 plus 19 is 35. And here, 26 plus 30 is 56. Very important to do the protons first. Now, to get the electrons, right, if it's uncharged like these two, the electrons and the protons would be the same. If it's charged, this means it has 2 more negative charges than positives. It has 16 positives, it must have 18 negatives. Okay? This means there's 3 more positives than negatives. It's 26 positives, so it must be 3 fewer electrons, 23. Right? Try a couple of these on your own. This is a place where you can hit hit pause and give this a go. All right, and then the next slide has the answers. So hit pause, I'll count to 5, and I'll go to the next slide. All right, did you try them on your own? Let's see how you did. Okay, so again, this is where you need a periodic table. For this class, all the stuff you're doing, you should have a periodic table on your desk. Put one on the wall. You can't see behind my computer, but there's one on the wall. All the cool kids have a periodic table on the wall. All right, so oxygen has 8 protons, it's number 8. Zinc has 30 protons, bromine has 35 protons. Then the neutrons, 18 minus 8 is 10, 65 minus 30 is 35, 80 minus 35 is 45. And then to get the electrons, oxygen 18, it's going to be the same. The zinc, there's 2 fewer electrons because it's 2 plus, so 28. The bromine, there's 1 extra electron, 36. All right, just a quick summary, and then let me see, and then we'll just go a couple more minutes here. All right, so atoms have no net charge. Number of protons are equal to the electrons. Ions are charged particles. All right, and there's positive ions are called cations, and for these, the electrons are fewer than the protons. I just went through this. Negative ions are called anions. It's not pronounced anion, it's anion, and that means there's more electrons than protons. All right, a couple more things here. So what's very interesting is how the properties vary. So if you look at these two, this is potassium metal, which is here, right? And this is potassium ion, which is here, a white powder. And you can see, just looking at these, the physical properties are very, very different. And yet structurally, they only differ by 1 electron. See that? For the chemical properties, if you want to click on this video, okay, this is potassium in water. I'll click on this one because it's really short. I think it'll come up. Give it a second here. There you go. All right, and a potassium ion in water doesn't do anything. So this caught fire. So you can see if you change the number of electrons, the chemical properties are extremely different. All right, I'm going to stop here to talk about isotopes, but I'll pick up here on the next video.